So this is part one of a new video series. This is day 4. We're dealing with geometry and measurement. So when we're talking about our geometry vocabulary, a lot of the beginning pieces of this video, we are going to discuss vocabulary, building blocks of geometry, our points, lines, and planes. And when we talk about a point, you're going to see it represented as a dot. There's no dimension to the dot. It's just a label. And so when you see that representation, that would be called point A. Now when we talk about a line, a line can be drawn through any 2 points. And a line has one dimension and extends infinitely in opposite directions. And we'll see an example here where we call this line AB, or we can call it BA. And notice the notation above the A and the B. You can create those in equation editor on Word, on a Word document. You'll just have to search for it. You go to Alt+ in a Word document, and you'll be able to look in different kind of those different pieces, different operations, different functions that you have within your equation editor that'll allow you to label something in a geometric mode. But if you have 3 or more points that lie on the same line, we call those collinear. And then points that do not lie on the same line are just called non-collinear points. You can see the example below. If they're all on the same line, collinear, then of course if you have that one that's not, then D is not part of that, so it would be a non-collinear. Part 6, so part of a line that begins at one point, so we're saying it's going to begin at point A and run forever in another direction, or we say extends infinitely in the opposite direction. We call that a ray. And the array is shown below, and it's labeled similar to the line. You got your differences. This would represent a ray, and this would represent a line AB, and this would represent ray AB. Part of a line that has a beginning and an end. So now that we're looking at an endpoint here, we call this a line segment. We have 2 endpoints here and here. And so notice how that's being labeled. So now we've got segment AB, ray AB, and line AB. So you can notice where the arrows at the end represent the line, the arrow on one end would represent the ray, and if there's no arrows on that segment, then we call it a line segment. So let's look at the distance and midpoint formulas. Distance formula is definitely something you can use when you're finding the distance between 2 points. If it's on a coordinate plane, we'll see that we can always use, or actually use, a variation of that with the Pythagorean theorem. So we'll see how that Pythagorean theorem and the distance formula work together. But that is, the distance formula is used to determine the length of a line segment. How far is this measurement? Well, if we know the endpoints, we'll be able to do that, because notice your formula is D equals the square root of x1 minus x2 plus the difference of y1 minus y2. So we're going to take the square root of the difference in x's, the difference in y's, and their sum. All right, so for instance, we've got point A, which is a negative 4, 2. So here's A, and B is going to be 6, 5. So I just want to know, well, what's going to be the distance from here to here? Well, since we know the points, if we look at the distance formula first. So distance is equal to the square root. Now let's take, it doesn't matter which two x values you want to start with, okay? You want to start with negative 4 and then subtract 6, that's fine. This is x2 minus x1, so I'm just going to start with the 6. So 6, take away negative 4, and then we're going to square that result, and then we're going to add the y2, which is we're coming back to get this 5 here. 5, take away 2, we're going to square that result. So now we get distance equals 6 plus 4 squared. We have to change the sign right here. So that's going to become a positive. Plus 5 minus, I'm just rewriting this. So distance will equal 10 squared plus 3 squared. Well, this is going to be 100 plus 9. So the distance is going to be the square root of 109. Now we have talked about estimating, and so we're thinking about, well, it's going to be between 81, other way, it's going to be between 100 and 121. So 109 is going to be somewhere around here. So it's closer to 100 than it is 121. And so that distance is 9. And 109, that distance is what, 12? So it's closer to 10, almost halfway. So probably a little less than halfway, so about 10 4/10 approximately. Now, a couple ways you can do this is you can use, if you're working at home and you don't have a graphing calculator, you can use, if you have an iPhone, you can go to your calculator and rotate it left or rotate it right and find that square root button. So you would just type in the square root of, or type in 109 and hit the square root button and then get your approximate value. Now let's say I'd mentioned something about Pythagorean theorem. Okay, so if we're looking at this segment here, I could use the Pythagorean theorem and figure out what's this distance here. Well, that distance is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that distance along the x is 10. Where have we seen 10 before? Well, that would be from right here. The distance on the y, or this length, is 1, 2, 3. So this is 10 and we're going to square it, and this is 3 and we're going to square it. So we've already seen 3 squared, which came from over here. And so that would give us 100 plus 9 is equal to c squared, which is, remember, the hypotenuse. And so we would get 109 equals c squared, so we're going to take the square root. So we would get the square root of 109, which we'll see is approximately 10 4/10. So a very similar approach. If you do not have a coordinate plane like this, then your best bet is to use the distance formula. If you have the line on a coordinate plane like this, you can use the distance formula, or you can use the Pythagorean theorem to find this. So next, we're going to look at a midpoint, which is the exact middle piece, middle section, middle point value of a segment. And that formula you'll see is right down here. We're looking for the distance we'll say of x1 and y1 and x2 and y2. So to find the midway point, which would be somewhere right in there, it's like you're finding an average between 2 points. A lot of times we do this when we're trying to find the median of data sets. And what happens if you have an even number of data values and you're trying to find the median? Well, you might have to find the number between 2 points, which is your midpoint. So you're just going to add those two up and divide by 2. And that's what you see here. You're going to add your two x's, divide by 2, add your two y's together, divide by 2. So let's do an example here. So we've got -9 plus a -3. Those are my two x values. And I'm going to divide that result by 2. Then I'm going to come and grab the two y values, -1 plus 7. Divide those by 2. So what's a -9 plus a -3? That's -12 divided by 2, which would be -6. So there's the midpoint. Between -9 and -3 would be -6. -1 plus 7 is going to be 6. Divide that by 2 and you're going to get 3. So the distance between -1 and 7 would be 3. So this is what would be your midpoint value. All right, let's switch to the topic of angles. And an angle is just a pair of rays with a common endpoint. And that common endpoint, like your absolute value graph, remember, that's called your vertex. And also on a quadratic, our minimum value or maximum value is also called a vertex. And that would be B would actually be the vertex of this angle. So we can measure it, or we can label this in different ways. We can say angle, A, B, C, or we can say angle C, B, A, or we can just call it angle B. In the diagram below, angles that share a side and a vertex, such as angle A, O, and C, and C, O, and B. These are called adjacent because they're next to each other, adjacent angles. And when you're measuring these, you're going to see that the measurement with angles will be in degrees. Okay. There's also a measurement in radians, but this is not the course for that. This will be, when we're talking about degrees, we're thinking about a protractor out of 360. So 360 degrees would be that circular total that make up a circle. So here we're talking strictly with your degrees, which would represent something in this format, 38 degrees or 135 degrees. And so when we're talking about classifying angles and their size, and we talk about acute is something we say is less than 90. So here's your example of that. As you can see, this angle here is less than 90 degrees because the right angle is 90 degrees. So now we're thinking, all right, well, if it's a right angle is 90 degrees, if you could close that, if you can close this 90 degrees some, now you're starting to look more like an acute angle. An obtuse angle is just taking this right angle and expanding it. So we see this measurement is more than 90 degrees, but less than 180 degrees, because 180 degrees is a straight line, also called straight angle, and that measures exactly 180. And then sometimes you'll see the word reflex angle. It's more than 180, but less than 360 degrees. So these are your different types of angles that we'll be discussing in this class. We also have different types of pairs of angles. So when I talk about complementary and supplementary, you can notice from the examples here that a complementary angle is this angle A plus angle B. Notice it's going to add up to be 90 degrees. And a supplementary, one would be obtuse, one would be acute, and it would add to give you that straight angle of 180 degrees. Now, when we have parallel lines and they're intersected by another line, that line is called a transversal. You can see that here. Now, when you have that, you start to create a lot of different angle measurements. So this line L is our transversal, and we may call this line M and line N. We're saying that line M and N are parallel, and line L is a transversal. Now we've created different angles. So we're just going to look at what is created. Okay, what's a corresponding angle? Well, that would be angle 1 and angle 5. Notice the relationship. Angle 1 and angle 5, they're on the same side of the transversal. So they're over here on this side of the transversal. Now we also have another corresponding side angle on the other side of the transversal. Let's look at 4 and let's look at 8. Let's look at 2. Let's look at 6. Notice they're all on the same side. Now 2 and 6 are both what type of angles? They're acute angles, and they're also in the same position. So 2 and 6 are corresponding, and they're acute. 4 and 8 are in the same position, and they're both obtuse. So they would be what we call corresponding angles. We could also say angle 3 and angle 7. Those are corresponding. Angle 5, angle 1, those are corresponding. So the idea is it's on one side of the transversal, actually the same side of the transversal. Alternate interior angles. Okay, the key word, alternate and interior. So we're thinking, when we say interior, we're kind of thinking inside these parallel lines. So when we say inside, now we're thinking alternating. So one's on one side of the transversal, one's on the other side. So 3 is on one side and 6. 3 and 6 would be considered alternate interior. And 5 and 4. So they're 3 and 6, they're both acute, and they're both alternating the sides of the transversal. 4 and 5 are both obtuse, and they are alternating both sides of the transversal. So we would say alternate interior angles are equal. 3 and 6 are equal. How do we know? Because they're alternate interior angles. Angle 4 and angle 5, they're equal. How do we know? We can also say congruent. Angle 4 and angle 5 are congruent. How do we know? Because they're alternate interior angles. Now, if we look at alternate exterior, now that's bringing in a different type of area. So now we're thinking anything out here is exterior to the parallel lines. So if we look at what's exterior, there's only 4 angles. Angle 7 and angle 2. Notice that they're both exterior, they're both acute, and they're both on alternating sides of the transversal. Angle 8 and angle 1, we'll say they are congruent. How so? Well, angle 1 is obtuse, angle 8 is obtuse, and they're both alternating exterior angles. And we know that alternate exterior angles are equal. All right, let's look at vertical angles. So what's an example of vertical angles? Angle 2 and angle 3 would be vertical. They're opposite. They're across from one another. And they have to be the same size. They're both acute. Notice that angle 1 and angle 4, they're both opposite of one another. They're both obtuse. Angle 5 and angle 8 are vertical angles. They're across from one another. They're both obtuse. Angle 6, angle 7 are opposite of one another, both acute. So you have multiple pairs of vertical angles. If you were going to list that vertical angle, you would say, well, angle 2 and angle 3. Alternate exterior, I would say angle 1 and angle 8, as these are just an example. Alternate interior, I could say angle 3 and angle 6. Corresponding, I could say angle 4 and angle 8. All right, now what about supplementary? Well, supplementary angles, remember, they add to give you 180. So angle 1 and angle 2 would both be supplementary. But so would 3 and 4. So would 5 and 6. So would 7 and 8. Those would all be examples of supplementary. And then I could go another direction. Look at 5 and 7. 6 and 8, 3 and 1, 4 and 2. Those are all examples of supplementary angles. Now you don't see any angles that are subdivided to where you see the vertical. You don't see anything like this where you notice that there's a 90-degree angle, so where you would have where you have complementary angles. We don't have it in this example. So, but we do have another one called a consecutive interior, and that would be 6 and 4. They're both consecutive. They're in line with one another, 4 and then 6, and they're on the same side, and they're in the interior. So angle 4 and angle 6 would both be consecutive interior, and then angle 5 and angle 3 would both be consecutive interior. And so they're similar to that supplementary. If you took angle 5 and set it next to angle 3, you would notice that they are would add to 180 degrees. So again, these are all examples of what type of angles are created when you take a transversal and intersect parallel lines. Next, we'll look at polygons. And a polygon, meaning a many-sided figure, and it will have 3 or more sides that form angles. And polygons are what we call closed figures. Okay, so I'm just going to pull up an example here of a triangle. Okay, triangle would be an example of something that's closed. Even a star has multiple sides, but it's also closed. this octagon, it's got 8 sides. It's a closed figure, so it would be a polygon. You could have a shape that looks like this. And then just notice that it's not closed, so therefore this would not be a polygon. So, this would be a polygon, this one, and then this would not be. All right, and then there's types of polygons, what we'll call a convex. Now it's going to have no line containing a side that has a point within the polygon's interior. So it's referring to this being the interior, okay? And if you'll notice, the interior here, there's no point, no vertex, no piece, no point of the point on a line. So see these points here, nothing is inside the interior of that polygon. Now here, we've got a point that lies inside that polygon. So it's closed. It is a closed polygon, but it's not convex. It's called concave because it does have a point in the interior. And so that's really just some things that you just want to recognize. If it's talking about a convex polygon or a concave, those would be your examples and the vocabulary that goes with it. Other types of polygons, all named by its side, okay? So triangle, you've got a quadrilateral, 4 sides, penta, so all the prefixes representing the number of sides, hex representing 6, hepta, 7, octa, non, deca. So you've got a nona, decagon, nonagon, octagon. These are all representing your different sides. So just the vocabulary again to represent that. Again, special types of convex polygons. Notice that all of these are a little different than the shapes that we see here. These shapes don't have any tick marks on the sides, but when you look here, they do. And so these tick marks are just representing, kind of giving you a heads up that this is what we would call regular. So this would be a set of regular polygons. And these are what we call equiangular. When we say that all the angles are equal. And then we'll say it's equilateral when we're talking about the sides. So again, the tick marks just representing that all those sides are equal, or you might see double tick marks. If they all contain the same number of tick marks, then you know that it would be regular. When you're looking at triangles, a triangle is a closed figure, and it's going to have 3 sides and 3 angles. And each side of the triangle meets the other to form a vertex. And then when we're thinking about a triangle, the sum of the measures, so we're talking about this angle and this angle and this angle, they should all add up to be 180 degrees. Now, a triangle can also be classified by the length of its sides. So notice here you've got a tick mark, tick mark, tick mark. This is why we call it an equilateral. All the sides. All sides of equal measure. And all sides have the same tick marks. Now we'll say something called isosceles. That just means that 2 sides have equal measure, and that would mean that only 2 sides that would mean that right here, only two sides have the same tick mark. This third side, see, doesn't have a tick mark because that means that that third side has a different measure. And then you've got another vocabulary called scaling, and a scaling just has no sides have equal measure, and you would see that all sides have different tick marks. So this one has 1, 2, 3 different tick marks, meaning different measurements. Now with a triangle, we can extend the lines, so you can kind of see the endpoints here, the vertices. And so an exterior angle to a triangle, it's the angle formed by, like I said, extending a side. And each interior angle is going to equal the sum of the other two interior angles. We'll look at this in just a moment. So let's say that, what we're saying here is that if this was, I don't know, let's say this one's 120 and this one's 40 and this one's 20. So 120, there's 160, there's 180. So all of them add up to 180. Well, if this one, see, this one's 20, so that means this one has to be 160. Well, notice that 160 is equal to 120 plus 40. This exterior is equal to the sum of the other two remote interior angles. All right, let's look at another color here. Well, if this one's 40, then that means this one has to be 140. And so if this one's 140, notice that the other two, 20 plus 120, should equal to 140. And if this is 120, then this one has to be 60. And if this one's 60, what's 20 and 40 added together? It's also 60. So any of those exterior angles, they're going to be the sum. The exterior angle will equal the two interior angles. Again, right triangles are a special kind of triangle where they only have one 90-degree angle. And then the sides opposite the right angle, the side opposite that right angle, which you're going to find any different type of triangle, no matter how small or large that is, you identify that 90-degree angle opposite of that is called the hypotenuse. And then the other two sides are called the legs. So this is the side opposite the other two sides. And the legs is not spelled correctly. So that would be L-E-G-S would be the legs. And then when two sides of a right triangle are known, we can use the Pythagorean theorem. Pythagorean theorem to calculate the measure of the third side. So this is your Pythagorean theorem, a squared plus b squared equals c squared. And I'd mentioned that, how this is kind of a variation of your distance formula. So if I'm using the formula of the Pythagorean theorem, A and B are legs, C is the hypotenuse. And this would just be an example where if you know one leg is 3 and the other leg is 4, how are you going to find this other side? How are you going to find the hypotenuse? Well, you would take A squared and B squared and figure out what c squared would be. So 3 squared is 9, 4 squared is 16. That's going to be 25. C squared is equal to 25, so I want to know what C is. So I'm going to take the square root of both sides, and I'm going to get 5 is equal to C. So 5 is the side length, and this was what we would call a 3, 4, 5 right triangle. Now notice as well that we had an addition going on throughout this whole problem here because we were looking for the hypotenuse. Now when you're looking for a leg and you know the hypotenuse, then what you would do is you would take a squared plus b squared equals c squared, and a we don't know, b is 10, and c is 14. We're going to end up doing some subtraction. So a squared plus 100 is equal to 144, or I'm sorry, 14 squared, which is 196. So I want to subtract 100 to both sides. So I'm going to get a squared is equal to 196. Take the square root of both sides, and I'm going to find 18 to be 4. A to be I'm going to find A to be 14. That would be if it was 196. Sorry about that. That's not, I didn't subtract the 100 from that. So that would be a squared is equal to 96, not 196. So that's coming back over here. A squared plus 100 equals 196. When you subtract 100 from both sides, you're going to get a squared equals 196 minus 100, which would be 96. Now I want to take the square root of both sides, and I'm going to find out that 96 is not a perfect square. It is somewhere between 100 and 81, and 96 is just 4 away, but 15 away here. So that's why you're going to see that not quite 10, but really close to it, approximately 9 8/10. Now, there's different types of right triangles, and there's special side lengths, and those special side lengths are called Pythagorean triples. Three, 4, 5 is known as a Pythagorean triple. So really you can take any multiple version of that. If you multiply all the numbers by 2, you're going to get 6, 8, 10. There's just another version. You multiply everything by 3, you're going to get 9, 12, 15. So any version of or multiple of the 3, 4, 5 would be a Pythagorean triple. So even if you took half of 3 and you got 1.5, half of 4 you got 2, half of 5 you get 2.5, that would also be a variation of the 3, 4, 5 because it is a multiple. You just cut everything in half. So a triple, Pythagorean triple, does exist when all the sides are whole numbers. You can look at what 1.5 squared would be, and that would be, let's see, 1.5 squared would be 2 1/4. 2 squared would be 4, and 2.5 squared would be what, 6 1/4. So if you add 2 1/4 to 4, you would get 6 1/4. So they are whole numbers, but you can have some that are decimals because I'm just looking at a variation, a multiple of my multiple just happens to be multiplying it by 1/2. Now, the Pythagorean theorem does work for finding right triangle problems and helpful for making things efficient for what we call special right triangles. And those special right triangles have different measurements, like a 30, 60, 90 or a 45, 45, 90. So with those triangles come special measurements. So we'll see that if this is 1x and this is 2x and this is the x times the square root of 3, well, side opposite 30, if we said was 1, the side opposite 90 is actually double that. And then notice on the square root of 45 and 45 that both sides opposite, right, have the same value. Well, square root of 2 comes into play that if you were solving for that hypotenuse and both sides were 1, 1 squared is 1, 1 squared is 1, c squared, this would be 2 equals c squared, so c is the square root of 2. That's where that square root of 2 is coming from. If one side is 1 and the other side I don't know, and the hypotenuse was 2, well, 1 squared is 1, 2 squared is 4, subtract 1, so a squared is equal 3. The square root of 3 would be this side length. So that's where those numbers are coming from in regard to the Pythagorean theorem. And it's where these numbers are being placed for different measurements if you're dealing with a special type of triangle, 30, 60, 90, or 45, 45, 90. So let's look at an example here. Just want to make sure we can think back on our special, if it's a 30, 60, 90. Remember the 30, it has this relationship of x, hypotenuse would be 2x, and x square root of 3. So it has that relationship. So if this is 60, and this is the hypotenuse, so if this is the hypotenuse, it has that relationship of 10 is equal to 2x. So notice this 2x here and 10 in that relationship should equal each other. So if 10 equals 2x, then that means x is equal to 5. Well, then that means that if this is the 30 degree, then that means this is 5. Back to the relationship up here. And if this hypotenuse is 10, then this is 10. So 2x is equal to 10. X is equal to 5. So how do we figure out what this measurement would be? Well, if we know that x is 5, then this side here would be 5 square roots of 3. So let's look at this second equation, triangle here. So if this is a 30 degree, then we know this is going to be a 60 degree. And we know that if this is 30, across from there is 2, that just means that the hypotenuse is double that. So if this is 2, then that means the u is equal to 4. Then how do we find v? Well, v is just going to be this relationship, right? X square root of 3. Well, we know what x is. X is 2. So this would be 2 square roots of 3 for v. So kind of go back here and fill in. If this is 2, then u is your hypotenuse. It's going to be 4, and v is going to be 2 square roots of 3. So everything is like I said, everything is basing off of this relationship of 3, the 30, 60, 90, with 30 being x, 90 being 2x, and the 60 being x times the square root of 3. Which, think about how that works with the 45, 45, 90, where this is x, and this is x, and this is going to be x times the square root of 2. So now let's look at this last one. This side here, this triangle here, it's modeling this relationship. So if the hypotenuse is 2 square roots of 6, notice what it's got to equal. Well, 2 square roots of 6 is going to equal x times the square root of 2. So we're going to divide both sides by the square root of 2 to figure this out. Well, 2 multiplied by square root of 6 is actually square root of 2 times the square root of 3. And then you've got this square root of 2. So this will divide out, and it's leaving you with 2 square roots of 3. So that's what this side would be, and that's what this side would be. And this long side should be 2 square roots of 6. Well, just to check that, if you've got 2 square roots of 3 plus 2 square roots of 3, they're both being squared, right? That's going to be equal c squared, which we know is going to be 2 square roots of 6. We already know the answer to that. But just to check it, 2 square roots of 3, that would be 4 square roots of 9 plus 4 square roots of 9. Well, square root of 9 is 3, so 4 times 3 plus 4 times 3. So that's 12 plus 12 is 24. And take the square root of both sides, you're going to get square root of 24, which will simplify to be the square root of 6 times the square root of 4, which would be 2 square roots of 6. So we're just using the relationship of what we know. We're going to look at this one here. We're looking at that relationship of x squared root of 2. And then that would be for your 45, 45, 90, but then your 30, 60, 90, notice that relationship. So keep going back to that relationship if you're going to solve a problem maybe in your homework or whatnot, or on a quiz, and it's giving you certain side lengths. Use that relationship and whatever's given in your example to figure out what x would be. All right, and then looking at quadrilaterals and similar figures. A quadrilateral is, again, it's a closed four-sided figure where the sum of the measures of the angles are 360 degrees. So all the angle measures inside, those would measure to be 360 degrees. So then you've got a trapezoid. Here's your figure over here. And so there's exactly two parallel sides, and the sides are not necessarily equal. That would be a trapezoid. Then you've got a parallelogram. Notice it talks about the opposite sides are parallel, and those opposite sides are equal lengths, and these would be equal lengths. So that would be an example of a parallelogram. We'll also say the diagonals. We would say here that the diagonals would bisect each other. Bisecting means that they cut them into equal lengths, here and here and here and here. A rhombus, as all the properties of a parallelogram, it has four equal sides. The diagonals are perpendicular. A square also has the same idea when you're talking about a rhombus and a square. They all have the same parallel properties of the parallelogram, 4 equal sides, and the diagonals are perpendicular. A rectangle, same properties of a parallelogram, 4 right angles, and the diagonals are congruent. So if we're making those diagonals would be the same length. A square, again, same properties. It is a parallelogram, has the same properties as a rhombus, and rhombi is plural, and it has the same properties as a rectangle. A kite, what we have, adjacent sides are congruent. So here, these 2 adjacent sides, those are congruent. These 2 adjacent sides, those are congruent. And then if you'll notice the diagonals do make, they are perpendicular. They do not bisect one another because the only one diagonal is bisected, and that would be this one right here. But the other one on the vertical end, that diagonal is not split into 2 equal sections. And then we'll look at, when we talk about similar geometric figures, they have the same shape, but have different sizes. So for figures to be, when we say congruent, their corresponding angles must be equal, and their corresponding sides must be proportional. So what do we mean by that? Well, if you look at this example, you've got triangle ABC and DEF. Well, both angle B and E are both 63 degrees. Angle A and D both have 36 degrees, and C and F both have 81. So they all have the same angles. It's just triangle DEF is larger in size because the sides are proportional. 10 is double 5, 8 is double 4, 4 is doubling 2. So it is 2 times the size of triangle ABC. So notice that when we compare 5 to 10 and 2 to 4 and 4 to 8, we're just saying that all of those ratios end up being half. So we would say that triangle ABC sides are half the length of triangle DEF, or we could say triangle DEF has twice the size length, because we could start at DEF and say, well, let's compare 10 to 5, let's compare 4 to 2, and let's compare 8 to 4. Well, all those are going to be equal, and they would all have a 2-to-1 ratio. So here, if I said solve for the missing measurements, I want to solve for y and I want to solve for x. So if I solve for x, I'm going to have to pick something. All right, I'm going to pick 16 and compare it to x, because those are the base segments of both triangles. So let's look at this one way. We'll try to look at it another way and solve it again. So 16 is the base of the small triangle. X is the base of the large triangle. I just want to compare that to 8 from the small triangle and 15 to the large triangle. So you see, sorry, that should be 10. I'm comparing 16 to X and 8 to 10. So this is a proportion, so I can do cross multiplying. So 8 times X equals 160. So X is 20. So I know this is 20. And then if I want to solve for Y, then I could start with Y, since that's the side between the 2 rings and the 3 rings here. So y would be compared to the other triangle between the 2 rings and the 3 rings, which would be 15. And then I can compare that to 8 in the small triangle, which is between ring 1 and 3. What's the other segment between 1 and 3 on the big triangle? That would be 10. So same idea, cross multiply, that's 10y is equal to what, 120? So y is 12. So we found x and y. Another way to look at this is if you wanted to redraw your figure. So I could say, well, here's the small triangle, and it has the ring, this is A and S and L. A has 1 ring, S has 2 rings, and L would have 3. Now, what are the side lengths that I know? Well, between 1 and 3 rings is 8. Between 2 and 3 rings is Y, and this is 16. Now, what about the bigger triangle? Well, this is going to be L. It's got the 3 rings. And O has 1 ring, and N has 2 rings. Well, the base between O and N is X. 1 ring and 3 rings is 10. 2 rings and 3 rings, that would be 15. So if you wanted to draw it, you just got to make sure that you're comparing the same angles and the same sides in order to be proportional. So another way to look at this would be, well, if this is 8 to 16, notice that 8 to 16 is half. So what does x have to be for 10 and that other number to be half? Well, x has to be 20. And so look at 10 and 15 and 8 and y. Those are other 2 comparisons that you could make. Well, if it's 8 to y and 10 to 15, then that's going to be 10y is equal to 120, so y again is 12. You're still going to find the same answers, just depending on how you compare things. And that concludes part 1 of this video series with geometry and measurement.